Recording is rolling. So here's here's my ambitions today anyway. I wanted to finish the chapter 5 puzzles with you guys, and then there's some other problems that I want to talk about. So let's see how far we can get on this. Right, so chapter 5 puzzles. Actually, last one we did was 24. All right. Okay, I think we're on number 37. All right, Tarzan. Right, you guys see Tarzan here? Oh, this one we haven't done yet, right? Right, so Tarzan swings on a vine that's this long, that's initially inclined at that angle with the vertical. What is this? His feet at the bottom of the swing. Say if he starts from rest versus if he pushes off. Now, you might have noticed. Where's? Hold on. This is gonna be one of your quiz questions, right? Here it is. Do you guys see number 8 on your quiz? This guy swinging on a pendulum, right? So we're about to pretty much do that right here. So number 37. Tarzan. Back up out here. Tarzan swinging on a vine. So he's starting here, and then he's going to swing down here like this, or something like that. Now they only told you 2 numbers. Well, and then part B, they say he kicks off some speed, but at the start there's 2 numbers. They told you the length. I'll make up a number. Let's say this is going to be like 7.0 meters, something like that. Okay. And they also told you the starting angle. Say beta is, call it 31 degrees, like that. And the question is, how fast is he going to be going, let's say, at the bottom of the swing? Right? Okay. Now, the framework for this is going to be conservation of energy, so maybe I'll get that going out here. The sum of energy at the top is equal to the sum of energy at the bottom, right? So energy is conserved. Right? Now, if I do that, energy is conserved, this implies a closed system, because if it was open, it'd have to say, like, the initial energy, plus some work is the final energy, but this is just energy is conserved. So what is in the closed system? And I'm thinking of 2 things. Tarzan and the Earth, right? Tarzan and the Earth, right? Okay. If he starts from rest up here, let's just do part A first. If he starts from rest, what kind of energy does he have right here? Potential energy. And do you guys remember the term for that? MGH. Has this kind of energy. By the time he swings down to the bottom, suppose you define the bottom to be height 0. Remember, you're allowed to define, if you're using MGH, like the localized version of potential energy, you're allowed to define height 0 wherever you want. So let's just make it the lowest point, because lowest point swing, right? Which means he would have 0 potential energy, simplifies it a little bit. Which means he has all what kind of energy? Kinetic. And you guys beat me to the formula here before I write it? 1/2 mv squared, boom. Now this is h at the top, and this is v at the bottom, right? So still vector, just call it, I'll call it plane v, but there's only one. All right. Now we're solving for this v. Right. Oh, this is going to cancel out the mass, which maybe not super surprising. Whenever you're just dealing with gravitational potential and kinetic, usually mass cancels out. Now, if you bring in a spring, it's going to be a different story. Right. So you can plug in a number for g, and if only you had the height change. Right. Let's take a look at how you would interpret that height change. Because he was up here. Right. Now he's down there. So isn't this the height change right here? Let's call it h. Right. I might even call it delta h, like a change in height, but let's call it h. Right. Do you think you guys could figure out what that height change is based on the length of the vine and the starting angle? Do some geometry. Right. I'll help you guys through this. This would be a really good puzzle question, just like throw you guys and like do for homework. But you guys are crazy good at stuff. So just have your brains turned on right now. And isn't this length of however many meters the same thing as this length from here to here? It's the same length vine, isn't it? Right? And do you guys see a nice right triangle right here? Nice right triangle. Throw a little right angle right here. Right? Ooh, if you do this leg of that right triangle, isn't the height just the difference between the full length of the vine and this leg of this right triangle? You see that? Okay. That's going to be our approach. Okay. So let's figure out what the segment of the right triangle. Right. How would you get that? What's this equal to? What times what? 7 meter hypotenuse multiplied by cosine of 31 degrees. Yeah. So in terms of variables, it's equal to L times cosine theta. But then if you pop in the numbers, you've got 7 meters times cosine 31 degrees. Good number for that is 7 cosine 31. Okay. Looking at, that's like almost exactly 6. Wow, okay. I wasn't really planning that, but that is cool. At 6.000 meters. Right. So, okay, so you guys know the height would be the difference between 7 and 6, right? So in terms of variables, it's L minus L cosine theta. Right? You could factor out in L if you want to, L times 1 minus cosine theta. Right? But it's just 7 meters minus 6 meters, which is 1 meter. Right? Wouldn't that be the height difference? Okay. Right, so go back up to here. Right? Now, if you want to solve this in terms of variables, which is a good thing to do for AP, I'm going to replace H with this expression. Right? L times 1 minus cosine theta. Right? And it's a good thing to be able to see where that comes from, and well, that would be the answer in terms of variables that you were given. Okay, guys, that? Right. All right, so cross multiply the 2, take the square root. And in terms of variables, V is going to be square root of 2g. Oh, hey, isn't it just square root 2gh? You see that? Square root 2gh, just like the Galileo problem, right? How fast was stuff laying in the base of the Leaning Tower? Square root 2gh. You guys see that poster right there? But h is now L 1 minus cosine theta in terms of the geometry. Yeah, so part of figuring out this problem is just to do the geometry of it all, right? And this whole bracketed stuff, height change, well, we did the numbers for it already. It came out to 1 meter. So this is square root of 2 times 10 meters per second squared for g times 1 meter height change. That's the square root of 20. Square root of 20. I'm looking at 4.47 meters per second. That's what it'd be, 4.47 meters per second. You guys get that? Right. That's part A. Right, okay. But there's a part B. The part B says, well, what if he kicks off with a certain speed? Like it says 4 meters per second, like that. Right. Now there's a right way and a wrong way to do this. Do you think, here, I'll pitch one suggestion to you guys. You guys tell me if you think this is right. If he kicks off at 4 meters per second, because here this assumption is that he starts off with 0 meters per second as his v naught. Okay, that's why it's all potential energy. Okay. But what if this isn't 0? What if it's like 4 meters per second? Can you say that his final speed at the bottom is going to be this speed plus 4, so it'd be like 8.47? Can you do that? Right. Hold on to that idea, because that's easy math, right? This plus 4 would be 8.47, right? But that's wrong. Okay? The proper way to do that will give you the actual answer is you have to do the full conservation of energy. So I'll show you guys that the answer is not 8.47. Okay? You guys want to see the right way to do it? Can you guys think of the right way to do it before I show you? Sum of energy initial equals sum of energy final. Thank you, Tom. Yeah, that's it. This here? This burn? Let's see, I think I might have a no, I don't see your name on, so does anybody know where that room is?
Yeah.
Yeah, where?
Yeah.
Yeah, can you show? Yeah, thank you, Warren. Right, so if he kicks off, what kind of energy does he have? And there's 2 kinds. He has the potential MGH, but doesn't he also have some 1/2 mv naught squared? Is that true? Okay. And then at the ending point, would it be all 1/2 mv final squared? Right? And we're still solving for the speed at the bottom. Yeah, thanks. All right, now, does this mass still cancel out? Yeah. Yeah, thanks, Warren. And let's multiply both sides by 2. Let's just solve in terms of variables, right? like you guys know that h is still the same geometry as before, L 1 minus cosine theta. Right. Make sure you can take that to heart, like be able to derive this geometrically. 1 minus, yeah, so L times 1 minus cosine theta is a height change for Tarzan. See, plus 1/2 v naught squared equals 1/2 vf squared. Multiply everything by 2, so 2gh, but don't write h, right? L 1 minus cosine theta. Plus v naught squared equals vf squared, right? And then finally, take square root of both sides. So vf is the square root of all that stuff. Right. Pause for a moment before I do this step. Okay. You guys remember 3 kinematic formulas from back in the day? Take a real good look at this last one. This last one is actually very closely related to conservation of energy. You guys may have been catching on to this last few days. Right. Vf squared equals v naught squared plus 2ax. You guys see that? See that's the same thing? Okay. All right, so to finish this off, that would be v naught squared plus 2g L 1 minus cosine theta. Like that? Is that good? Okay. Let's start plugging and chugging in. So you guys know g is 10 meters per second squared. There's a 2. We got L was 7 meters in my made up numbers. You guys have a different number for your 1 minus cosine of 31 degrees. And then plus, now here's where, that's how you incorporate the speed. Right? You can't just tag the speed on like I was saying before. You have to square it and then add it and then take square root, which is going to be a different value. They said it kicks off at 4 meters per second, so I'll just keep that same value, right, as the textbook. Like that. This giant square root equals VF. So VF equals, you can squeeze it right down here. All right. So part of this trick is to figure out, can you plug this in the calculator? You can check it down in smaller parts is always fine. I'll do it all in one go. So 4 squared plus 2 by 10 by 7 by 1 minus cosine 31 degrees. I'm looking at, 5.9997. I'm going to round that to 6.0 meters per second. Okay. Okay, so just to recap this. Okay. Given these numbers, 7 meter long, fine, 31 degrees from the vertical. Okay. If he swings from rest, he only picks up to about 4.47 meters per second at the bottom. Okay. If he pushes off at 4 meters per second, he doesn't go up to 8.47. No. He only picks up to 6 meters per second. Okay? Because you have to do this whole process. Okay. Conservation of energy. Okay. You guys get it? All right, next one. All right. Now we did 38. Just we did the outlet. Okay. So this one, number 53. The electric motor of a model train accelerates the train from rest to this many meters per second and this many milliseconds. Guys, milliseconds. Isn't that rolled back the decimal 3 places to get number of seconds? The mass of the train is this many grams, because you have to convert to kilograms before you do any math. Find the average power during the acceleration. Okay. So 2 ways to get power. What's that?
We did this one.
Oh, we did? Okay. Thanks. Did we do this graph?
I think we started it, but we didn't fully finish on 60.
Oh, is that what we did? Okay. All right, so 53. They gave it here. Let's start with the variables. They gave us the mass. No. Yeah, they gave us the mass of the train. Okay. No, they gave it to us in grams. I'm going to make up a different number and turn it into kilograms. I'll use something that's pretty close. Okay, so some number of kilograms for the mass of the train. They told us the initial velocity was 0, started from rest. They told us the speed it picked up to in milliseconds. So I'm going to make up my own number, but some number of seconds, like tiny number of seconds. And they also told you I'm so sorry. Yeah, what's up? Oh, yeah. Okay. I'm so sorry, guys. This is scratch that. they straight told you the meters per second. So let me do something like this, meters per second. Okay. The time interval, that was in milliseconds. So let's call this like, something like that. Okay, what was the power to do that? Well, I see a change in kinetic energy. And isn't change in kinetic energy provided by the work done on the train? Right? It's called work energy theorem. Whatever work you do on the train is going to translate into its kinetic energy if it doesn't go up in hills. Right? And isn't power work per time? Like that? Wouldn't that be true? Right? And where's the work come from? Well, it comes from the change in kinetic energy, which, so it's like delta KE, or delta K, I should say, divided by the time interval. So we're looking at 1/2 mv squared. I'll just call it 1/2 mv squared because the starting is just 0, so just subtract 0. Okay. Divided by time interval. Power. Okay. Right, so that's going to be power is 1/2. The mass of the train was a given value. Here's my number, example number. They told you the final speed of the train. So here's my number. Okay. Don't forget to square that speed, and then divide that all by the time interval. Okay. You guys did all the conversions also, right? To turn into kilograms and seconds and all that stuff. Okay. So that times that squared, all divided by that. Okay. I'm looking at this many watts. Okay. It would be watts, wouldn't it? It'd be watts. Okay. You guys get that? Some number of watts. No, since my numbers are not radically different from your numbers, you should be getting a number that's kind of in the ballpark. You guys get something kind of like that? Okay. I want to point out, there's a question I got asked you guys, number 5. You guys see number 5 on your take-home places, an elevator with some mass is pulled up with some acceleration. When it's going some particular speed, what's the power of the motor pulling up the elevator? Well, this one just made me think of that, so you guys had to do that real fast. So elevator, what if it has, okay. What did I tell you? Okay. I told you the mass of the elevator, and I told you its acceleration, okay. And I told you also its velocity. Okay. And let's just have everything going upward, keep it pretty straightforward, right? Okay. So you guys know that power is work per time. Okay. But isn't that also force times distance divided by time? Okay. And when you express it like that, I told you, I did tell you guys this before. I remember, how many of you guys remember this from your notes? You could also call this what times what? Force times velocity, right? Because d over t isn't that like velocity, right? This is an alternate form for power. This is all power. Power is that, power is that, okay? Like this leads to this, leads to this, right? Is that, right? Now, guys, if you have an elevator that's accelerating, then isn't there extra tension in the cable that's more than just the weight of the elevator? Like if I do a free body diagram, here's the weight of the elevator pulling down, mg. Here's the tension pulling up, called F sub t, like a tension force, right? Doesn't the tension have to be greater than the weight to accelerate it up? So this force that it say is being provided by this motor at the top of the elevator shaft, it's more than the weight of the elevator. Do you guys remember exactly how much more? You guys remember it's mg plus or minus a? You guys remember that? Right. No. If this is an FRQ, don't just jump to that. You have to derive this from a free body diagram. Say like, this force minus this force divided by the mass, it leads to this. Okay? But just save a little time, then you guys can do that. Okay. So then, which one is it though? Is it plus or minus? Accelerating up. Yeah, plus. You'd have to put extra tension in the cable. Okay. So then, just start plugging in those values that they give you. Bum, 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 bum. You guys can do that, right? Okay. Okay, I think we did the graph already too, didn't we? Did we do this one? Okay, that's what I was thinking. Okay. All right, so 3 objects. It's number 89. Got a fancy looking modified Atwood. There's some M2 here, there's some M1 here, And so we got a big ol' M3 over here. Okay, and then these tied together, maybe thrown over pulleys. That whole thing, right? Okay. All right. They gave you the values of those masses, and they also said that there's some friction. Now, specifically between M2 and the surface. Guys, if M3 is greater than M1, which way is this gonna rotate? Clockwise or counterclockwise? It's gonna pull clockwise, right? If it starts from rest, it'll go clockwise. Okay. Which means that the friction on M2 acts which way? To the right or to the left? Has to be to the left, right? So just sort of free body diagram. I know that there's a friction force to the left. Okay. And they told you exactly how many newtons of friction that was. They gave you a number. Okay. Now there's of course also other vectors going on. Well, here, I won't draw all the vectors. Each of these has a weight. There's a normal force on them too. You guys know that, right? I should just for completion. Okay. M2G, F sub n. Okay. You guys know that. The other ones also have some forces. Okay. All right. Use energy conservation to find the speed of one of these blocks after it's moved down some distance, okay, after some height change. Call it h, right? Like from here to here, it's moving down. Okay. Now, whatever speed this is, isn't the same speed for all the blocks because they're all tied together. So they always all have the same speed, they're all tied together. Okay. So let's do energy conservation. The sum of energy initial equals the sum of energy final. Okay. Actually, I do have to modify this. It's not a closed system, it's an open system because it's friction. Okay. So don't have to say minus the work done by friction. Okay. However much energy starts with, take away that work done by friction, you'll end up with some amount of energy left over. Is that true? Okay. So what is the starting energy? And we did a similar type one in the on that 3-page energy table. Isn't the fact that M3, the heavy one, is going to follow this height, it's providing that potential energy? So I'd call it M3GH. Right? Your textbook gave you the distance it would follow, so that's what H is, right? Now, work done by friction. Hey, what's the formula for work? What times what? Force times distance, right? And since they directly gave you that friction number, they did. They said it's 30 newtons, something like that, right? You could just directly plug that in. And then, oh, what distance would that act over? H, right? Now, it's not truly a height change, right? It's block 2 sliding to the right, but it does move that distance, doesn't it? Here, maybe I'll even label that. Right? That's the distance that this block moves to the right. It is distance h, isn't it? It's the same thing. However far this one moves down, this one moves to the right that much. Right? Right. Now, if they did not give you this friction number, you guys know how you, let's say they gave you coefficient of friction. You guys know how you can get it? Okay. So this weight is equal to this normal force. Normal force times coefficient of friction would be friction force. But they did give you a number anyway. Okay. So whatever energy is left over from that, this one falling, take away the friction. Okay. The energy is going to go, I'm thinking 4 different places. No. 1. Yeah, 4 different places. Right? What's one place the energy goes? How about into lifting block 1? Right? So block 1 has to be lifted. Oh, what height? Also h. Isn't it true that block 1 is moving up that height at the same time? Right? They all move distance h. Right? One's going down, one's going to the right, one's going up. So that's one place to go. Where are the other 3 places that the energy is diverted to? Exactly, each of the kinetic energies. Okay. In fact, since they all have the same speed, if I want to make this a little simpler, can I just say plus 1/2 times the collective mass, m1 plus m2 plus m3 times v final squared? Isn't that true? And the question is, what is that v? Okay. So there's actually 3 energy terms here. I just factored out the 1/2 of the v squared. Okay. Through some like collective masses, maybe. Okay. They told you each of the masses, that many kilograms, and then boom, boom, boom again. They told you those. They told you the height change, boom, boom, boom. Gravity, make up a number either 9.8 or 10 meters per second squared. Boom, boom, that goes there and there. Right? And they also gave you the friction force. They said so many newtons of friction force. Okay. So see how you have everything, you can just solve for v? But while you guys are calculating that, I'll make up some of my own numbers and I'll see what this would be. Okay, so what if I had, like 10 kilograms, 10 meters per second squared? See if you guys can beat me to the answer. Okay. I'm gonna have a 2-meter height change. Let's have 20 newtons of friction force for the same 2 meters. Okay. And then I'll make M1 like, I don't know, let's call them 1 kilogram, I guess. 10 meters per second squared, 2-meter height change, plus 1/2. All right, I needed them 2. Let's go 5 kilograms, I guess. Okay. Yeah. So 10 by 10 by 2. Okay. So I had 200 joules in my system. Take away the friction. That's minus 40 joules. Now I'm down to 160. So I've got 160 joules to go around. I'll subtract off the energy lifting block 1. So there's 20 joules. So now I'm down to 140 joules. Going to 1/2 mv squared. So times 2 divided by sum of the masses looks like 16 kilograms. Okay. Then square root. Oops, square root. Okay. Right. So with my made up numbers, I just got V final equal to this many meters per second. Okay. All right. So here are some example numbers for that problem. I think that's, did I hit all the main homework problems? I think I did, didn't I? I hit all of them? I didn't miss any, right? All right, good deal. Let me double check your guys' quiz real fast, make sure there's nothing I want to talk about here. Here, let's flash this up real fast. Okay. So, can you guys interpret a force versus distance graph? You guys can do that, right, for spring? Okay. Oh, number 2, that looks pretty similar to what we just did, doesn't it? Number 3 is a proportion one. Number, okay. I'm gonna leave that one to you guys. Okay. Number 4, we talked about it a little bit yesterday. Remember, it's basically your very last AP classroom question, number 4. Okay, so if you look at number 16 from your AP classroom yesterday, basically that one. Okay. Number 5 I talked about earlier today. That's the elevator accelerating upward. Oh, number 6 is the question I should have asked instead of the spring question for last quiz. So we'll call that a review question for this time. Do you guys remember how to do orbital speed? Orbital speed, right? Based on the mass of the planet. Right? So that's it's hanging on a poster back there. I don't think I have it within reaching distance right now, but. Or alternatively, for number 6, you could go to Newton's modified version of Kepler's third law. Right. So there's a couple of approaches you can get for number 6. Right, number 7. Okay, this one I wanted to talk about with you guys. Okay. Yeah, let's do it now. Number 7. Right. So you see this block spring through this loop? Like going through that loop like that? Okay. Do that one. Okay. Actually, I got a whole new poster for this. We drag this out real fast. Here it is. Here it is. All right, this right here. So I really like this because it's a closed system, if there's no friction. Closed system consisting of the spring, the block, and the earth. So this would be called a block, spring, earth system. Okay? And it has 3 different kinds of energy in it. But otherwise, it's pretty fundamental, right? So the energy stored in the spring when it's compressed, distance x, ping, go into 2 places by the time it gets to the top of the loop. Here's my initial point, my final point. Okay? One place it went into was lifting the block against gravity. That's potential energy in VH. And whatever energy is left over, however many joules, is all going to go into its speed. Right? Isn't that true? Okay. I got a side question for you guys before I start chugging through the any math on this, which is most of the time, I know we make a lot of simplifications in this class. Like there's no air drag, or sometimes there's no friction, or sometimes there's, but one of the simplifications we usually do for, say, like some kind of roller coaster looking problem is there's a straight track leading into a perfect circle, but I didn't quite do that here. You guys see here how it's kind of a teardrop looking shape? You guys see that? And if you guys ever go to a theme park and you see a roller coaster, you'll actually see that. You never see a straight track leading into a perfect circle. Just in like physics notes, but you usually see something that looks like a teardrop shape. I had one student yesterday in my honors classes when I asked them this, who was able to figure out why. Why would you never design, say, a roller coaster to go from a straight track into a perfect circle? That's a very terrible engineering idea. Why do you have to have This is called a spiral. See how, here, I'll give you guys a little bit of a hint. You guys see how going into this, it's a very large radius of curvature. You can fit a circle that looks like that right here into this part. Right? But by the time you get to the top, the radius of curvature is much smaller. It's like a circle we fit right here. Right? Why is that spiral a much better design? Yeah, Warren.
It's much easier to get the coaster to go all the way around instead of stopping and rolling back or anything tragic.
Yeah, okay, yeah, so something to do with its motion. Yeah. Okay. How about this? You guys remember centripetal force, like mv squared on r? Okay. If you went from a straight track directly into a perfect circle, wouldn't that centripetal force just like bam hit you all at once? You sure wouldn't that be like really jarring? Yeah, you wouldn't want that. That's why you want the spiral, so that there's a small centripetal force with this very large radius of curvature, and then it gets bigger as the radius of curvature gets smaller, because mv squared divided by r, right? Okay, sure. Right. Same thing with traffic design. If you're ever a traffic engineer and you're designing roads that are like winding around, you never want to go from a straight road into a perfect circle, even though in this class in the notes we do that, but realistically you want to have like a spiral shape. Okay, that's a side thought. So take a look at this. The question I asked you guys is, well, let me tell you what I asked my honors classes. My honors classes, I told them K, X, M, G, H, and I asked them to solve for V. So that's just a plug and chug kind of question, right? Now you guys asked a higher level question. I asked, if you change K by some factor, and you also change H by the same factor, then how would V respond? So what energy is left over to go into V, right? Okay. Now, let's think about this. Let's do a factor of 9. I don't think I asked you guys that. Right. So if you pump up K by a factor of 9, you make the spring 9 times as stiff, right? And then you also make the height change a factor of 9, so make this loop 9 times as tall. Ooh, that's a lot taller, isn't it? So yeah, this would be a factor 9, this would be a factor 9. Would the equation also be balanced if this kinetic energy term was also increased by a factor of 9? Right? Right? Right. And to do that, what would what factor would go on V to accomplish that? And it's not 9, it's not a factor of 9. Okay? Right? If you guys can figure that out, and you look at your own question, which is very similar, I think you guys can figure that one out. Okay? You guys got that? Any questions on that one? Okay. Great. And speaking of roller coasters, I've got a roller coaster question for you guys that involves conservation of energy. Now, this is a really classic physics question. So, got a roller coaster, drop off a hill, and I'm going to do something that I just told you guys never to do. Right, so, if you guys ever design roller coasters one day, never do this. Never have a straight track leading into a perfect circle, because that would be really jarring as a rider. That centripetal force would just like bam all of a sudden. But let's make believe, because we're just doing like simplified physics. Right. Suppose that I have some roller coaster up here with some mass sitting on a top of a hill of some height h. Naturally, the question is going to be what is this height? So we're going to solve that. Okay. Say relative to right here. I'll call this height 0 at the bottom. Okay. So there's some h that we're eventually going to solve for. Okay. What's the minimal height, I should say, so that by the time the roller coaster is like has reached the top of this loop right here, it has sufficient speed to make it around the loop. I'll label that V. Now you have to know something else. You have to know the radial size of the circle. So I'll call this R. Okay, what we got? Right, so how about it? Here's what I do real fast. I'm going to switch my screen over and show you guys a video of this sort of. You guys see that bowling ball at the top of that track? Okay. So let's see later. We'll actually drop this thing. Okay. So it goes down through this loop. Oh, okay. It made it all the way around. So good news for that guy wearing the helmet. Okay. But okay, right there. Okay, it got real close. Right. What if the bowling ball like ran out of steam right at that point? Would it just fall off the track and onto this guy's head? Okay. So imagine a dash line straight horizontal. What if you dropped it from a part of the track that had the exact same height? Wouldn't that be the case that it, okay, so it gains kinetic as it's going down, losing potential, but then it picks up potential, loses kinetic as it's going up. Wouldn't it run out of steam at exactly that height and fall down and hit him on the head? Right. So if you dropped it from that height, that wouldn't be high enough. It better be higher than that, shouldn't it? Right. Now a little twist on this. The fact that the bowling ball itself is rotating is also an extra piece that we're sort of ignoring, but we'll talk about that in the future, probably December. Right. But aside from that, you still would have to draw it from a higher height than the actual coaster itself, wouldn't you? Okay, so go back up here. Okay. What is, you guys need this, what is the height of this loop in terms of variables that are already written on the page? 2r, good call, 2r. You guys see that's 2r? Right, so geometry puzzle for you guys. Right? So h has to be bigger than 2r, doesn't it? Right. Okay, let's solve this with conservation of energy. Sum of energy at the top of the hill is equal to sum of energy at the top of the loop. So initial to final. Okay. Right. So okay. Now what kind of energy at the top of the hill? MGH. Okay. What kind of energy at the top of the loop? You've got both mg times 2r plus, there better be some speed, 1/2 mv squared, right? Because that's, you better have a speed, right? Otherwise it's not going to make it around. Okay. And speaking of that, this problem actually combines conservation of energy with what we did last, which is something to do with rotational motion. We've done enough rotational motion, you guys can do this. Okay. Let's think about the free body diagram of this coaster right at the top of the loop. Okay. Free body diagram. Okay. What's one force on that at the top of the loop? Yeah, normal force and also the gravitational force, its weight. Okay. Now I'm going to label its weight mg. Okay. And you're right, you should also label the normal force if there's sufficient speed to get around. Okay. But tell you what, since we're solving for like the minimum height to make all this happen and it just barely gets around, what do you think happens to that normal force, which would be pressing down, right? You guys seen this free body diagram before? Right. If it just barely gets around, what do you think that normal force approaches? 0, right? So that it would just be its weight that's keeping it on this curved path just at that one instant. Okay. So that would be like the tipping point. That's what we're gonna do. So what we're gonna say is that the centripetal force is provided by only the weight. Okay. It's usually plus normal force, but we're letting the normal force just go to 0. Okay. So it's just the weight. And do you guys remember the formula for centripetal force? mv squared divided by r. You guys remember that? Okay. The AP equation base says v squared over r is centripetal acceleration, so you guys can just multiply that math and get that. Okay. That's only being provided by the weight. Remember, centripetal force is never a force unto itself. It's always provided by something that's already there. In this case, the weight. Okay. And usually plus normal force, but we said that goes to 0. Is that okay so far? Okay. And why am I doing all this? I'm doing all this so I can figure out what is the minimum speed in terms of these other variables, so I can plug that into there. Because remember, this thing has better be in motion, have some kinetic energy, but how much? How much is going to be diverted into that? That's being answered by the centripetal stuff. Is that okay? You guys follow that? Okay. All right. So let's hone in on V. Try to solve it. Oh, what's going to cancel out both sides? Mass. So it doesn't matter if it's an empty cart or if it's full of passengers. The minimum speed you need to make it around the loop is whatever it is, regardless of the mass. Right? Cross multiply the r. I'm going to get v squared is equal to gr. Okay. Now, I could go the extra step and say v is the square root of gr, which might be a good thing to do, but I'm going to stop right there because I would just end up squaring that anyway to plug it back into this v squared. You guys see that? That's just going to feed in right there. You guys got that? All right, so that's the last of the physics. Everything else is just algebra. You guys got that? Like, if you got to this point, then you've mastered the physics part. Okay? All right, so we got our mgh, supply of energy, is going to go into 2 places. It has to lift the coaster against gravity to the top of the loop, so that's 2 mgr. Okay, see, I just took the 2 and pushed it out front. Okay. Plus an additional 1/2 m, and then v squared collectively is gr, right? I'll throw it in brackets to show there was a substitution there. Okay. So we got 3 terms. Okay. Oh, guys, what's going to cancel out? The mass. So again, it doesn't matter if this part is loaded with passengers or not, right? Or how many funnel cakes they ate. You still need the same minimum height. Okay. What else cancels? Gravity field. That means something. That means that if you took this whole coaster to the moon, how would the answer change? Would you need a taller hill, a smaller hill, or the same height hill? The same height hill, because it doesn't matter what the magnitude of the gravity is, as long as you have gravity field, right? So the answer to this on the moon is the same as it would be on Earth. H equals 2r plus 1/2 r. Altogether, that's 2.5 r. Okay. Assuming no frictional losses, of course, right? So no friction. Okay. So if there's no frictional loss, if that's like an air hockey table sort of. Okay. You guys get that? Okay. Now, the difference between this and that video you just saw, like if you want to get the video problem exactly right, you also have to say, well, the bowling ball was rolling, so there'd be one extra kinetic energy term. Actually, that is a perfect segue into something else that I want to clean up. Okay. You guys remember this 3-page energy table? Okay. Now, I'm not going to have you guys turn this in. I gave you guys points in the gradebook for this already, you may have noticed, but there were a couple of rows that we hadn't got to. And yeah, this is exactly what I want to talk about next. So a ball rolls without sliding down some hill length L. Rolls without sliding. Okay. So this is getting a bit into future content, but I'll plant some ideas, and then when these eventually come around, like, oh, these eventually roll around, it's just like, oh. You guys say, oh yeah, I've sort of seen this before. I kind of remember some of this. Right? So some energy is going to go into making this thing roll as it goes down. I'll tell you guys what. If there was no friction, if this is just a pure air hockey table, then there would be no rolling at all. This thing would just go down. It would look really weird, even though it's a rolling object. It wouldn't roll. But there's going to be static friction, and I know it's static because see it says without sliding. Okay. And static friction actually will not take energy out of the system. And what system am I talking about? We need the rolling ball, we need the earth, and AP might even throw in the hill, right? Because there's a force from the hill to get it to induce the rolling, but it doesn't actually take energy out of that system. So you could actually call this a closed system at every time. Okay. So what kind of energy at the start? MGH, just at the top of the hill. Right? The table set up to ask the question, how fast is it moving at the bottom? That's usually the question you get. Like, how fast is it rolling at the bottom? Right? Now, do you guys think that if you had a bowling ball that was solid all the way through, and a basketball where all the mass is on the surface, versus, let's say, like the solid cylinder rolling down, do you think that those would roll down differently? Like somebody would win the race, and that somebody would have different speed at the bottom? Okay, that is true. Now again, all the energy is conserved. So if you had like another incline going up, say there's like gradual slope, if there was no frictional losses, then it would do this. It would go roll, 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 and it could just do that forever without frictional loss. Okay. But those rolling objects would be different. Like the basketball would take forever to roll back and forth, and the bowling ball would go a lot faster. Okay. So what's the energy mix at point B? Well, obviously you got some 1/2 mv squared, kinetic energy, but I'm going to start calling that translational kinetic energy. That's to say like energy in a straight line, because there is some energy that gets it to rotate. Now what is involved there? Now here's where we're getting a bit into future content. You guys remember this work page I gave you a few weeks back? It tells you linear motion variables and then the rotational equivalents. Now we just looked at the top half of this just to do some kinematic work. Here's one that I haven't got to yet. Mass in kilograms. Mass in kilograms represents two things in AP physics. It represents gravitational mass, like a gravitational tug. But before that, remember, it represents inertia. So if you push on something with some force, the more mass it has, the less it wants to accelerate. What about a rotational context? Like if you put a force at the edge of some spinning object to get it to rotate, that's called torque, by the way, also from the future. Then how's it gonna respond? Rotating. It's probably really hard to get the basketball to rotate because all its mass is near the edge. So it says some of them are squared. Like if you broke the basketball down to like a million different points and then like added up each part in m/r squared, you get some calculus. So I'll talk about that in the future. But for us right now, what's important is that that's the equivalent of inertia, but in a rotational context. Right? And you guys remember how the rotational equivalent of speed, like velocity, is like omega, like angular velocity? How fast this is like spinning like this, like radians per second. Right, so do this. Say plus, because some energy is going to be diverted into rotational kinetic, 1/2 I omega squared. See how that looks like 1/2 mv squared, but it's just the rotational equivalent popped in. Okay, so that is that's the full setup. Okay. Now, if you want to solve for v at the bottom, there's actually a way you can do that. You guys see a hint there in gray ink that says omega equals v over r. Okay. Now this is something we've also talked about too, so quick reminder. Okay. You guys remember a couple of Roosevelts spinning around, and they have the same angular velocity, they have the same omega, the same turns per time, but the one that's further out has a greater linear speed, doesn't it? If you point a radiogram at it. Okay. And how can you go from one to the other, from omega to v? Well, you guys see how this coin is, let's do it this way, 5 centimeters from the center. This one's 10 centimeters from the center. Right? So v, linear speed, is equal to omega times r. Right? So if it's twice as far out, it's going to have twice the linear speed. Right? You guys know that from before. Right? So do the math on this. Right? We're going to do sum of energy at the top of the hill equals sum of energy at the bottom. Right? We'll do this one, then we'll be done for today. Right? At the top of the hill, it's all mgh. At the bottom of the hill, it's a mix. It's translational kinetic plus rotational kinetic. Right? And that I has different values depending on, is it basketball, a bowling ball, solid cylinder? So we'll worry about that in the future. Okay. But we can sort of finish this because that omega is the same thing as v over r. Right? Let's say that this v and this omega are not independent of each other. They're actually related to each other. Okay. Let me factor out the v squared. 1/2, say, m plus I on r squared, v squared, like that. Okay. Cross multiply by 2, divide all the bracketed stuff down, take the square root. Looks like v is going to be, well, it's going to be the equal square root. And we have a 2mgh, and then divide by all the bracket stuff. Okay. Okay. And then in the future, we'll talk about what that I means more exactly, but you know what all the other stuff is. Right? So yeah, that's the speed of some rolling object going down the hill. If you know what rotational inertia is. Okay. You guys get that? All right. Yeah, phew, I got through my agenda. That was my ambitions for today. So tomorrow, I've got a fun lab lined up for you guys. We're going to break out those spring launchers. I'm going to have you guys tomorrow measure or calculate what is the spring constant of those launchers. All right, you guys have a good Wednesday.